All right, we're going to talk about foundations now. Last time we covered retaining walls a little bit. I'm not going to talk about retaining walls for a while, but you are expected to know everything we've previously covered about retaining walls. Okay, so I want to go back again. I'm going to spend some time reviewing what we learned in the previous semester, and but we're going to extend it considerably beyond what we learned last semester. But I want to refresh your memory. We had, for instance, we had a mat with basement type foundation, and what we did was we wanted to figure out the region, the soil region that was stressed, and what we did was we drew a pressure bulb, a depth of 2B, this is the width B, below the foundation. And what we wanted to do was use the this region here that has been stressed. We're going to find the center of that region in the vertical direction, and that point was going to help us determine what the settlement of the structure was. And we're going to do something similar here. We're interested in finding the settlement of these different types of foundations. So this was last semester. I'm going to call that this semester a type 1 foundation. And that's mat and basement is type 1 foundation. I'll tell you what I mean by type 1 and type 2 in a minute. Another type of foundation is one that looks like this, and that is with end-bearing piles. So I'm going to call this a type 1 foundation. Again, and it has end-bearing piles. What are end-bearing piles? These are my piles here, and end-bearing means that we are transferring the load entirely to the tips of the piles, and that means that our pressure bulb goes down a depth 2B below the tips. And then those are the type 1 foundations. We've already talked about those to a certain extent. This semester, though, we're going to add in a basement with these end-bearing piles, which we did not do last semester. Now, what we're going to call a type 2 foundation is like this here. So in this particular case, what we have is that the foundation base does not go through the entire structure. It just goes underneath the columns. And this is, we have what's called a pile cap here. And the piles come down from the pile cap. This is, we're going to call this a type 2 foundation because we are going to have this width B. In other words, the width B is not this entire width of the structure. Instead, B is the width of the pile cap. So the pressure bulb goes down from the tips. Again, we're using, these are end-bearing piles, and it goes down a distance of 2B. Well, the B is much smaller than the entire width, so what we're going to find is that the pressure bulb doesn't go as deep now, and sometimes that can be a big advantage for us, because if we have, for instance, a very soft soil down here, we can avoid stressing that soft soil using this type of foundation here. It doesn't work all the time, but sometimes we can do that. So what we're saying, so for this purposes of this class, so that it's easy for us to talk about these, is I'm going to call a type 1 foundation where B is the entire structure width, and a type 2 foundation where B is the footing, we're going to talk about footings, or the pile cap width. So two different types, I'll call them type 1 and type 2, just so it's easy for us to discuss them. Okay, so to refresh your memory, I want you to calculate out, or we're going to calculate out the point of interest depth and the H, which is the thickness of the compressed soil, or the thickness of the soil that we're going to compress, I guess is a better way to say it. How did we do this? It's pretty straightforward. Here are my steps. The first thing that we did is multiply 2b and get the distance 2b, and we draw 2b pressure bulb below the tip. So this is for our end-bearing pile. So in other words, I draw something like that, and that is a distance of 2b. And that's the first two steps. Then what do we do? Then we're going to shade the clay or silt region in the pressure bulb. Well, in this particular case, what are we seeing? This is the clay in that region. This is gravel. We don't stress, well, we do stress the gravel, but the gravel does not compress very much. So compared to the clay, the gravel doesn't compress at all. So we don't really consider the gravel in our calculation of settlement. So I'm only interested in the stressed clay region. And then we're going to find the center of the shaded region. So, conceptually it's like that. For the second one, what is it? Well, then I draw my 2b here, and then I find the stressed silt region, and then I find my center of the stressed silt region there. So the steps are, if you remember these, to basically find the depth to the bottom of the pressure bulb. We find the depth to the top of the clay or silt, and then we take the depth of the pressure bulb plus the depth of the top of clay divided by 2. That gives us the point of interest depth, and then we take the difference between those two, and we get our region H. If you remember, I didn't show the H, so in other words, this would be the H. This is the essentially thickness of the clay that will be compressed. So we want both the depth, the point of interest, and H. So what I want you to do is pause the video and complete these two tables for these two problems. So go ahead and do that. Okay, I'm assuming you've done the problem. I'll just fill it in here. So this is 60, so 2b is 120. If I go down, this is at 31, so 100 plus 31 is 151, so I get the depth of the bottom of the pressure bulb is 151. Then the top of the clay is here, it's 41, so I get that. And then we just do a simple calculation. 151 plus 41 over 2, 151 minus 141. That gives me 96 for the point of interest depth, and the H is 110. What does that mean, the H? There's my H right there. It's 110 feet. That tells me I'm squeezing about 110 feet of soil, and then the point of interest depth of 96 is in here, so that we're saying that center of that region is approximately an average. It shows us a little bit of an average behavior over the depth of the clay region that is stressed. Now we do for the second problem. My B is 12, so 2B is 24. I go down 24 below the tips. The tips are at 20. 20 plus 24 is 44. So we get our depth at the bottom of the pressure bulb of 44. we have the depth to the top of the clay or silt is 24. I then, sum those two and divide by 2. Gives me the point of interest depth. The difference between the two gives me the h. So in other words, notice that h is right there. That's 20 feet. So we have both our point of interest depth and our h for the two different types of foundation. Okay, I want you to do these. So why don't you pause the video and do these two problems. All right, I assume that you've done them. Now we have a little bit of a trick with this one. For the first one, what do we find? Well, when I take the 2b is 100. 2 times 50 is 100. There's my 100. It goes down below the tips, which are at 32, so I go to 132. Well, what happens when I hit 132? So 132 is in the rock. Well, that's not, if it's in the rock, well, that is not going to be, we're not going to compress the rock, so I'm not interested in that. So we have to pay, I'm throwing in another little trick here, in that my actual, so there's really the bottom of my pressure bulb, my depth of my pressure, because I'm not interested in the pressure bulb down here. So really the depth of the bottom of the pressure bulb is 120, not 132. And the depth of the top of the clay, it's obvious, is 43. So I'm using those two numbers and take the sum, divide by 2, take the difference, and I get my two numbers, the point of interest depth and the h. So in other words, in this case, this is my h right here. So I have to watch out to make sure to see what happens with my pressure bulb. And so pay attention to going into rock, or if this could be gravel or something like that. That's another issue. So you have to pay attention. We're only interested in the region of the silt or the clay that is stressed. If we're stressing rock, gravel, sand, we don't want to include that. For this one, my B is 20, 2B is 40. I go down there, since the tips are at 30, I'm now at 70 feet. So I have my depth of my pressure bulb is 70 feet, and then the top of the clay is right here, 38 feet. So I'm going to use those two numbers. The sum divided by 2, the difference, and I get my point of interest depth is going to be in the center there, and my h, there's my h, it's 32. So, okay. All right, I want to talk about the different types of foundations then, how we're going to lay them out for this class. This is a little bit special to this class, but I found that if we separate these foundation types into two, then we can, it just makes it a little easier to do these calculations. So what we're going to call a type 1 foundation, for instance, we have a mat with basement, which we've already talked about. And then we're looking at end-bearing piles and piers beneath the entire mat. So, in other words, I put my piles beneath the entire mat. And we've looked at these. Now I want to throw in another one, which we're going to call friction piles and piers beneath the entire mat. So we have end-bearing piles and piers, we have friction piles and piers, and I will explain to you the difference between the two and how we're going to handle them differently for settlement analysis purposes. So this is the type 1 foundations. The key is that everything goes beneath the entire mat. We use the entire mat, our B is equal to the building width. So, maybe I can even write that in there here. That B is equal to, for our building width, for a building. And the second type, well, what we find is B is equal to the footing or pile cap width. So, so our type 2 foundation, the first one we're going to look at is footings. Well, footings we haven't quite talked about yet, but very simple foundation is you have the building column and you just put, a pad, base for that column. We call that a footing. And we don't need to do, under some circumstances, this is the cheapest by far foundation. You can see that we don't need a whole mat. It's far less concrete, a lot less effort to put in footing. So if we can get away with footings for our structure, we've come up with our cheapest foundation type. So, if you can do this, if this works out, that's good. It doesn't work out in a lot of cases, so that's why we have other foundations. So what else are we looking at? End-bearing piles and piers beneath the footing or pile cap. So this is what we talked about earlier. We have underneath each column we have a pile cap, and then we extend our piles or piers. I'll talk about the difference below the pile cap. So we have end bearing, and then we also have friction piles or piers beneath the footing or pile cap. And again, for the type 2, B is equal to footing or pile cap width. For type 1, B is equal to the building width. Just a little chart about piles and piers and deep foundations so let me just talk about this briefly. There are lots of them. In a nutshell, I show this because there are lots of them in a practical sense. There are many different ways to build these types of foundations. I'm not going to go through them for our purposes. Well, they in a practical sense, they're quite different. But the way that we're going to handle them is we're going to look at them as being very similar. So let's just look very closely. So we're looking at load-bearing, what they're calling load-bearing piles. What do we have? We've got concrete, we've got steel, we've got timber, we have composite. Composite being two different types of materials, maybe concrete and steel, for instance, where the upper part could be concrete and the lower part is steel, or vice versa. If we more information about, for instance, steel, what do we have? We have an H section. In other words, H section is like an I-beam in the ground, a hollow steel. What could it be? It could be like a tubular or pipe-ish or a box. And then this table also has a pipe over here that could be filled or unfilled. In other words, sometimes you can have a pipe, fill it with concrete. That would be in this category. You can have an open-ended, you can have closed-ended. All these. Now this is where. Okay, so that's steel. So this is my groups of steel. Concrete. What we are going to call piles, just to make life simple, are precast. In other words, we take the concrete pile is created off the job site, brought to the job site, and you have a pile on site, and then it is inserted into the ground, driven, pushed, different ways to get the pile into the ground. So they're precast. We're going to say precast concrete are piles. We're going to call these also piles, all the steel piles. So what we're going to call piers are the ones that are cast in place. What do I mean by cast in place? We can drill a hole, for instance, drop in a rebar cage, fill it with concrete, and then we have what's called a cast in place foundation. And we're just, to keep it simple, we'll call that piers. Again, for our purposes, we are simply going to say that piles and piers behave similarly. When you get into more details, they can behave a little bit differently, but for our analysis, we are going to take them as being very similar. So now the cast in place, the piers, drilled foundation, there are lots of names, put it that way, is about all I can tell you. But the main thing you need to know is this one arrives on site already made, as does this. This one you've got to make at your job site. So that's the primary difference you need to know. And if you can look at this, you can see that sometimes they're cased or uncased. In other words, sometimes you drill a hole and pour in concrete. Other times you have a casing, for instance, a steel casing, and then you pour your concrete inside the steel casing, for instance. And all these for the cased. You have driven, I'm not going to go into all these details, but you can take a look at all the different options of getting these into the ground. And then similarly over here for the uncased, cast in place. So those are the cast in place. All right, I want to say something about, for instance, the pile cap. And this is just some layout. What happens is, for instance, you can have a square pile cap, and then typically you have your column coming down the middle, and you have, for instance, 4 piles around the perimeter. But it doesn't have to be a square. It could be a hexagon, and then you have a different pile arrangement under the pile cap. You got all different shapes. You can see them. You can see them here. Rectangles. Different options. Anyway, the idea here is to give you a concept of, we have the column, which is generally, maybe in the middle as much as you can, and then around the columns you have below the pile cap you have the piles. So I want to make a comment as to how to determine whether a pile is end-bearing or friction. We talked about end-bearing, friction. Well, what's the difference? Well, it all depends on the soil type at the tip. If the soil type at the tip is coarse-grained, so if it's sand or gravel, we have end-bearing. If it's silt or clay, we have friction. So if you look at this, so in other words, there's the tips of my piles right there. There's the tips of my piles right there. If this layer is coarse-grained, which means, sand or gravel, then we have end-bearing. If it's fine-grained, then we have friction. So the way to determine whether or not you have an end-bearing pile or a friction pile is you simply look at the soil type at the pile tip. So the soil type at the pile tip determines whether the pile type is end-bearing or friction. I'm not going to go through this in a lot of detail. We covered it last semester. But I just want to review quickly on how to get the using the pressure bulb, how to get the stresses. So this describes what we covered last semester. I'm not going to go through it because it takes too many words. Just go ahead, pause the video, read this, refresh your memory, and go back to last semester's lecture. They're available. And but the main thing that I want you to know is that when we go into the pressure bulb, we're going to look at 3 different points below in the pressure bulb diagram. We're going to look at one below the center, one below the edge at the same depth, and then we're going to look at one that's halfway down below the center. So we've got it. This is all you need to know. You look at that point, and that point on your pressure bulb diagram. And remember, you read off the contour. So in other words, if you look at point C is approximately on the 0.7 contour. Point A is between the 0.3 and 0.4 contour. So maybe it's 0.35. Point B is between the 0.2 and 0.3 contour. So maybe it's 0.25 or something like that. But, okay, so we read that off. I just want to remind you of one other thing. And that is, for point C, we look at the contour, we had 0.7, but then we have to divide by 4. That's what the previous slide showed, is that we have to divide that by 4. So, I'm not going to go through why that is, because we covered it last course. And so, but I just want you to remember that we're going to look at these 3 points, A, B, and C. C, we have to take the contour divide by 4. And this describes that point A is below the center at ZF over B. Point B is below the edge at ZF over B. Point C is below the center at ZF over B. Divide by 2. And then you must divide the contour value by 4 for point C. And you should memorize this. But here's the catch. I want to emphasize that use this only for type 1 foundations. We're only going to use these 3 different points for type 1 foundations only. This is important. This gets people messed up. We're not going to use those 3 points for type 2 foundations, only for type 1 foundations, and we'll see why that is a little bit later. So this is an important point. Use A, B, and C only for type 1 foundation. What we're going to find is that we're only going to use point A for type 2 foundations. So type 1 foundations use A, B, and C. Type 2 foundations, you're going to use only point A. Okay, so I'm going to let you do this problem. This is all review. And we're going to find the point of interest, H, and the stress increase at the point of interest beneath the center, edge, and corner. So we're going to do all 3 points, and you got to start out with first finding the point of interest depth, the H, and then you're going to fill in this table like we did last semester. So I want you to pause the video here and fill in this table. Okay, I'm assuming that you've paused it. Now you've done the work. Now we're going to fill in the table. So the first thing we're going to know is the tips are in gravel. So we have end-bearing piles. That means that we draw the pressure bulb from the pile tips, which is at 21 feet. So we get that, I guess I didn't draw that out, but what do we have? We have the, the building width is 25, so we're going to have, so that's 25, so that's 50. We go 50 feet, which means that 50 feet plus the 21 takes us down to 71. So we're going to have that the depth to the bottom of the pressure bulb is equal to 71 feet. And the depth to the top of the clay is 32 feet. And so we can find the point of interest depth is going to be what the sum of those two, 71 plus 32 over 2, which is 51.5 feet. So that's the POI depth. And then the H is going to be the difference between the two, which is 71 minus 32, which is 39 feet. So that gives us the two values, the point of interest depth and the H. Now we're going to fill in these values, and we're going to have the piles at the center, edge, and corner. Well, what do we, the load, P, is what? The weight of the structure. 2.5 million pounds. What is the area? The area is what? 25 squared, 625. Q is P over A, so I just go P divided by A, 4,000 for all of those. Then what do? I take my Z. Well, how do I compute my Z here? Z is what? Well, the Z is the distance from the base, if you remember this, the base of the structure to the point of interest. Well, the point of interest is 51.5 feet. So the pile tips are at 21, so what do I have? 51.5 minus 21 is 30.5. So my Z, if you remember how we use the pressure bulb, we have to use the Z. So my Z is 30.5. That is for points A, for our first points A and B. The center is A, the edge is B. How about point C? Well, when I go into my pressure bulb, what do I need to do? I need to take that 30.5 divided by 2 is 15.25. My B is what? My B is the whole thing. My B is the width of the whole thing. So that's going to be 25. I just then compute Z over B. That gives me that. Gives me those numbers there. And then I go into my pressure bulb to get my factor. So I go 1.22 below the center, 1.22 below the edge, 0.61 below the center. But then again, I have to divide by 4. So 1.22 below the center is there, and that's between 0.2 and 0.3. 1.22 below the edge is there, and it's pretty much on 0.2. And then here's my corner, so A, B, and C. Corner is half of that, and it's pretty close to 0.6, but what do I have to do with that 0.6? I've got to divide by 4. So I get 0.25, 0.2, and then 0.6 divided by 4 is my pressure bulb factor. So when I want to come up with my delta sigma V, what do? I multiply my pressure bulb factor times my Q. That's going to give me my delta sigma v. So 0.25 times 4,000 is 1,000. 0.2 times 4,000 is 800. 0.15 times 4,000 is 600. This is what I want, that last column, and that's pretty much why we did this particular exercise. Okay, and then the last thing I'm going to do, okay, so for the previous structure and the given soil property, so find the settlement at the center, edge, and corner. So now this is our problem. We just did it. And let's find the settlement. Here are I'm giving you another piece of information, the soil properties, the water tables at the ground surface, so I've only given you gamma saturated. I give you C epsilon R, C epsilon C, the OCR. So we have our soil properties. Then what do? Well, let's fill out this table here. So here's my solution. And there's my soil properties that I'm interested in. First thing I have to do is figure out my sigma prime I. Sigma prime I is what before the structure exists. So I've got my depth and my point of interest, the sigma v, the u, sigma v prime, OCR, sigma prime p. So I need my sigma prime I and then get my sigma prime p. So how do I get my sigma v? Well, so again, that's my point of interest. My sigma v is what? It's before the structure exists. So I just take the soil layering before the structure exists at my point of interest. And what do I have? I've got, let's just go back to it. I've got silt, I've got gravel, and I've got clay before the structure exists. So I've got 15 feet of silt, 17 feet of gravel, and 19.5 feet of clay. I add those up, I get 5770. The water table's at the surface, so it's going to be 51.5 times 62.4 for the pore pressure. And then sigma v minus u gives me sigma v prime. That gives me my sigma prime I. That's my sigma prime I is right there. To get my sigma prime p, I'm going to use the OCR times the sigma prime I. That gives me my sigma prime p. I get 2760. And then now my goal is to get my sigma prime f for center, edge, and corner. So again, here's my sigma prime I is 2556. Sigma prime p is 2760. Our goal is to fill in my settlement equation. There's my base equation right there. C epsilon R log sigma prime p over sigma prime I plus C epsilon C log sigma prime f over sigma prime p. There's my, that gives me the strain, epsilon v. And then epsilon v is delta h over h. Our goal is to get delta h, which is h epsilon v. We've already calculated out the h. So previously we calculated out the delta sigma v for the center, edge, and corner. 1,800, 600, we just did that. So what do? I have my sigma prime I is 2556. I add 1,000, 3556. Then I take the 2556, I add 800, 3356. The 2556, add 600, 3156. So very straightforward to get the sigma prime f's once we've computed the delta sigma. Once we've computed these delta sigma v's, it's very straightforward. And then what do we need to do? Well, we need to create our plot, if you remember how to do that. So this is for the center, this is for the edge, this is for the corner. I do my bilinear sketch here. And if you remember, what do? When we do those sketches, the first point we put on is our sigma prime p. So I put on my 2760, it goes at the corner of our little bilinear plot. And then we look at the sigma prime I, my sigma prime I is less than the sigma prime P, which means it goes to the left. So in each one of these, it's going to go to the left. Then I look at my sigma prime F, and where does that go? Well, in each case, each of the sigma prime F's are bigger than our sigma prime P. So all of these go to the right. We now have our sketch, and what we see from our sketch is that we need to use both slopes. We need to use both slopes for these. So I'm not going to go through it in detail. You can all do this. I have my C epsilon R. I've got my C epsilon C. And then I do my logs. The beginning part is the same for every one, 2760 over 2356. So that's all the same for all of them. But then and the denominator for the second part is the same, the 2760. It's just that my numerator now is going to be 3556, 3356, 3156. So we can get those, and then we simply plug it in, do the calculation, plug it in, and get our epsilon v's, and then my h's. So we get my h epsilon v. H we did previously, and so let's see, what was our h? Our h was 39 feet. So we multiply that out. We get, these are my delta h's. And then let's see. So I guess just to complete this, what we want to do is this, with this structure, find rho and rho over L. So, and we're going to use rho over L as 1 over 300 as acceptable. If it's greater than that, then it's not acceptable. Remember, rho is the differential settlement. L is the horizontal distance between the 2 points. So here's our footprint. If you remember, then we're going below the center, we're below the edge, and we're below the corner. And so the L that we're going to use is this horizontal distance. From center to edge, it's half of the 25, which is 12.5. For the center to the corner, well, you got to use the Pythagorean theorem to get the L, but everybody can do that. So, yeah, so in other words, L center to edge is that. 12.5, using the Pythagorean theorem, we get 17.68 for the center to corner rather. So what I want to check out my row, center to edge, center to corner, edge to corner. All right, so here are the calculation. These are the values we just came up with. And now we just plug those in, center to edge. So center to edge is what? Center edge. And here's the L. We have 1 over 40.3. Okay, so, and then we have what? Center corner. Center corner. And there's my L. Then we have edge corner. Edge corner. And then, of course, and then that's that L. Again, that L is going to be 12.5. So we get these values, and what do we find? We find these values. They're bigger than my 1 over 300, so this particular foundation does not work. We have to make some adjustments. And we'll talk about what to do when you encounter this. You go, we can't build this. We have to. That's what the design process is about, is figuring out what works and what doesn't work. And if it doesn't work, then you try something else. It's pretty much a trial and error process. You do trial and error with your engineering judgment, you'll get there. It takes a while to build the engineering judgment, but after a while you'll get it. Okay, we're going to stop there.